Start the chapter 4 today with elementary number theory and methods of proof being the chapter. Section 1 is the direct proof and counterexample, the introduction to it. Both discovery and proof are integral parts of problem solving. You think you've discovered a certain statement is true, try to figure out why it is true. If you succeed, you'll know that your discovery is genuine. If you fail, you can learn from that. You can learn why the statement is false. The interplay between discovery and proof is not reserved to the end of the problem-solving process, but rather is an important part of each step. So you look at it. Now, direct proof and counterexample. Assumptions for this chapter. Assume you're familiar with the laws of basic algebra. I'm pretty sure everybody here is at least to the calculus level, Cal 1 at least. So these basic premises are assumed to be true. There's no integer between 0 and 1, and the set of all integers is closed under addition, subtraction, and multiplication, which means that sums, differences, and products of integers are also integers. Substitution, transitivity, that sort of thing is all true. Even, odd, prime, and composite integers. An integer is even if and only if n equals twice some integer. An integer is odd if and only if it is equal to twice some integer plus 1. So n equals 2k for even, n is equal to 2k plus 1 for odd. Definitions of odd and even to justify your answers to the following questions. Is 0 even? Well, it would be 2 times 0, which are both integers, so it would be even. Is minus 301 odd? Yes, because for minus 301, if your k is 151, it would be 2k plus 1 to make 301. And 151 is an integer, so it would be odd. If a and b are integers, is 6 times a to the second power times b even? If you factor out a 2, you get 2 times the quantity 3a squared times b, which is an integer. So an integer, 3a squared times b is an integer because it's a multiplication. Multiplication is closed on integers, and it's 2 times an integer, so it would be even. If a and b are integers, is 10a plus 8b plus 1 odd? Yeah, because you factor out the 2 from the first 2 elements, you get 5a plus 4b times the quantity times 2 plus 1. 5a plus 4b is an integer by the definitions before. So it would be 2k plus, fall into the category of 2k plus 1. Is every integer either even or odd? That's a little bit more complex. Not immediately apparent. Oh, whoops, wrong direction. Yes, the explanations for the previous yes answers, but the last one, yes, every integer is either even or odd. However, the reason for this fact is not immediately apparent. It can be deduced by using the method of proof by contradiction. It is also a consequence of the quotient remainder theorem. If you, seems like it would be there'd be other ways to show it too. But definition, an integer n is prime if and only if n is greater than 1. And for all positive integers, r and s, if n equals rs, then either r or s equals n. An integer is composite if and only if n is greater than 1 and n equals rs for some integers r and s where r is between 1 and n and s is between 1 and n. Basically, a prime it can be divided by itself or 1 and that's it. Composite is more than 2 integer factors. So, is 1 prime? Nope. It doesn't have 2 factors. It only has 1. The number 1. So a prime number has to be greater than 1. Is every integer greater than 1 either prime or composite? Pretty much, yeah. And write the first 6 prime numbers. Would be what, 2, 3, 5, 7, 11, and 13. And the first 6 composite numbers, 2, 4, 6, 8, 9, 10, 12. Something like that. A prime number is required to be greater than 1. And is it is an integer, let n be an integer greater than 1. Consider all pairs of positive integers r and s such that n equals rs. There exist at least 2 such pairs, namely r equals n and s equals 1, and r equals 1 and s equals n. Moreover, since n equals rs, all such pairs satisfy the inequalities of those given. So all numbers are either prime or composite. If n is prime, then the 2 pairs are the only 2 ways to write n equals as rs. Otherwise, there exists a pair of positive integers such that n equals rs and neither r or s equals 1 or n. So n would be composite in that instance. Those are the first 6 prime and first 6 composite numbers. Proving existential statements. Well, proving an existential statement, one way to prove it is to find an x in the domain that makes the predicate true. Another way is to get a set of directions for finding such an X. Both of these methods are called constructive proofs of existence. Logical principle underlying such proof is called existential generalization, which says that if you know a certain property is true for a particular object, then you can conclude that there exists an object for which the property is true. Just kind of common sense there. Prove if there exists an even integer n such that it can be written in two ways as a sum of two prime numbers. Let's just do that one. And skip B. So proof A: let n equals 10, and 10 equals 5 plus 5. 10 equals 3 plus 7. 3, 5, and 7 are all prime numbers. Thus, there exists an even integer, namely 10, that can be written in two ways as a sum of two prime numbers. You just need to show that one exists. A non-constructive proof of existence involves showing either one, that the existence of a value of x makes q of x true is guaranteed by an axiom or a previously proved theorem, or two, that the assumption that there is no such x leads to a contradiction. Proof by contradiction. The disadvantage of non-constructive proof is that it may give virtually no clue about where or how x may be found. The widespread use of digital computers in recent years has led to some dissatisfaction with this aspect of non-constructive proofs. And it has also led to increased efforts to produce constructive proofs containing directions for computer calculation of the quantity in question. So it's hard to program non-constructive proofs. So disproving universal statements by counterexample. So a universal statement is for all x, just choose one, find one x where the hypothesis is true and the conclusion is false. That is a way of disproving a statement by counterexample. Just one example that proves it wrong. I'm reminded of a quote by Einstein. A book came out written by 100 authors saying that Einstein was wrong. And when asked about that, and he said if it was wrong, it wouldn't require 10. All it would require is one author to show that it was wrong. So proof by counterexample just needs one example of it being wrong or false, and you prove it. Disprove this statement by finding a counterexample. For all real numbers a and b, if a squared equals b squared, then a equals b. Got an example of that? A counterexample? Or is the statement true? It's false. Why? Give me an example of why. would be equal to the square of the positive its absolute value. Yeah, so negative 2 and 2 as a and b. A is not equal to b, but a squared plus b equals b squared. So, yeah, that's a counterexample. Fact that both positive integers and negative integers have positive squares helps in the search. Only need one such pair to give a counterexample. Disproving by counterexample is done in this way, in this format. Proving universal statements. The method of exhaustion. Not going to go through all the examples here, but let n be an element of integers. If n is even and n is between 4 and 26 inclusive, then n can be written as a sum of two prime numbers. Well, exhaustion is taking all the even numbers between from 4 to 26 and writing them as a sum of two prime numbers. And there you go. If you have a very large set, the proof by exhaustion can be time consuming. Or if the set is infinite, it is impossible to show by exhaustion. The most powerful technique for proving a universal statement is one that works regardless of the size of the domain. It's based on a logical principle sometimes called universal generalization. Or generalizing from the generic particular. To show every element of a set satisfies a certain property, suppose X is a particular but arbitrarily chosen element of the set and show that X satisfies the property. So, at some point in time, you may have been shown a mathematical trick that, like the following. You ask a person to pick any number, add 5, multiply by 4, subtract 6, divide by 2, and subtract twice the original number. And then the final result is 7. Well, you can prove it by picking a number and going through these steps and show that for all x, no matter what, or in this case a box, no matter what box is chosen, what value is chosen for the box, 7 is the remaining quantity. So that's a generalization. The x in the table above is another way of representing the number the person picks. It is particular because it represents a single quantity, but is also arbitrarily chosen or generic. So you can generalize from the generic particular to conclude that if you follow the steps, you'll always get 7, regardless of the initial value. When the method of generalizing from the generic particular is applied to the property of the form, if P of X, then Q of X, the result is the method of direct proof. So the method of direct proof is 3 steps. Express the statement to be proved in the form of every X is that's an element of D. If P of X, then Q of X. Start the proof by supposing X is a particular but arbitrarily chosen element of D, for which the hypothesis P of X is true. Basically, it means suppose x is an element of D and P of x. Show that the conclusion Q of x is true by using definitions, previously established results, and the rules for logical inference. Prove that the sum of any two integers, even integers, is even. A direct proof. Good idea to ask yourself whether you believe it to be true in the first place. In this case, you might imagine some pairs of even numbers like this and check that their sums are even. However, since you cannot check all pairs of even numbers, you cannot know for sure if the statement is true in general. Making a property hold for many properties that hold for a large number of examples still fail to be true in general. So it's not a democratic thing where if it's a majority of them are true, then it's true, but rather it's if all of them are true. For the statement in general, you need to show that no matter what even integers are given, their sum is even. Given two even integers, it's possible to represent them as 2r and 2s for some integers r and s. Distributive law of algebra, factor out the 2, and then because rs is an integer, this statement is true in general. Suppose the statement to be proved is much more complicated than this. What method can you use to derive a proof? The statement is universally quantified over an infinite domain, thus to prove it in general, you need to show that no matter what two integers you might be given, if both of them are even, then their sum will also be even. How should I start the proof? What am I supposing? This gives you a starting point. Then ask yourself, what conclusion do I need to show in order to complete the proof? Since both involve the term even integer, you must use the definition for this term, and thus you must know what it means for an integer to be even. It follows from the definition that m and n are even, each equals twice some integer. One of the basic laws of logic, called existential instantiation, says in effect that if you know something exists, you can give it a name. You cannot use the same name to refer to two different things, both of which are currently under discussion. It's kind of like scope of variables in a computer program. You can't use the same variable name in the same scope twice to mean different things. So the sum of any two even integers is even by that direct proof. Getting proofs started. Believe it or not, once you understand the idea of generalizing from the generic particular and the method of direct proof, you can write the beginnings of proofs even for theorems you do not understand. The reason is that the starting point and what is to be shown in a proof depend only on the linguistic form of the statement to be proved, not the content of the statement. The first and last sentence of a proof, write the first sentence of a proof and the last sentence of a proof. Every complete bar-type graph is connected. You have the formal restatement here, and that would be the starting point. The conclusion to be shown is just the conclusion of the if-then part of the statement. In this case, G is connected. So suppose G is a graph such that G is a complete bipartite. Conclusion to be shown, G is connected. Thus, the proof has the following shape. Fill in the blanks to prove the following theorem. For all integers R and S, if R is even and S is odd, then 3R plus 2S is even. How are we doing on time? 2:45, okay. All right. For all integers R and S, if R is even, S is odd, then 3R plus 2S is even. Now prove, you have to show that 3R plus 2F is even by A, R is 2N, and S is 2N plus 1 for some integers M and N. Then by B, these letters will be shown in a later slide. Then this is true by substitution, and this, multiply it out, gets this, factor out the 2, and you get this, and that is 3m plus 2n plus 1 is an integer. So because of C, and the definition of it, these are the this where t is an integer, this equation is even by the definition of even, and A, B, and C, where from the previous slides, are the definition of even and odd. Substitution, products of sums and sums of integers are integers, all accepted facts. And I believe that wraps it up for the day. A little basic number theory and direct proofs. Proving by counterexample, that sort of thing. Anyway, have a good day. See you on Thursday.